Hi, my name is Naja Agarwal, and my project is recognizing the applications of magnetism in microplastic extraction. The main question that my project is planning to answer is how can the applications of magnetism be effectively utilized in the extraction of harmful microplastics from water samples? Before going into this project, there was a lot of research that had to be conducted. Plastic, a prevalent part of everyday life found in the packages we buy, used in the creation of goods and materials, and in the technology that we rely on, poses an immense threat to Earth. According to the IUCN, plastic comprises 80% of marine debris taken from surface waters and deep sea sediments. This is the most common type of debris found in the ocean. Microplastics are detrimental to the environment, posing an immense threat to marine life. Microplastics were first described in the early 1970s through the work of Professor Richard Thompson, OBE. Plastic, more particularly microplastics, are non-biodegradable. Microplastics that source from larger plastic debris never fully degrade. They fragment into minuscule pieces that accumulate in bodies of water over time. The degree of fragmentation can result in the creation of microplastics that can be 150 times smaller than a human hair, virtually undetectable. Microplastics are everywhere, in our food, in marine ecosystems, and at every level of the food chain. Arctic whales are suspected to be consuming hundreds of thousands of microplastics. Beluga whales show that there is movement of microplastics through the food chain. In recent studies, hermit crabs have been shown to be affected by microplastics. Their natural behavior for competition is expanded because as they seek larger shells throughout their lifespan, they are shown to have an impairment in competitive behavior and also an impediment in their ability to secure suitable shells for survival. Scientists have worked to find more effective and sustainable ways of extracting microplastics from the water. Physicist Arden Warren has dedicated much of his career to cleaning oil spills. His understanding of magnetism and chemistry inspired him to attempt to magnetize the oil and separate it from water. This technique is more environmentally conscious and does not expose soaps and chemicals to the ocean. This liquid was called ferrofluids. Visual results of ferrofluid microplastic extraction are indicative of the effectiveness of this method. They can be tested using spectrometers that are capable of accurately measuring the concentration of microplastics by passing a spectra of light through contaminated and tested samples. Why is this relationship important? Plastics are becoming far more prevalent in oceans and waterways. They have many health concerns attributed to them, and the decision going forward is that the environmental dangers are now being brought to the attention of the public. If action is taken now, it can ensure that a solution prevents further damage to the planet's wildlife and ecosystems. My hypothesis is that a magnet of a greater pull force will be able to more effectively remove microplastics from water samples. On the basis of size, smaller fragmented plastics will be extracted most effectively. Polyethylene terephthalate and low-density polyethylene will be among the easiest plastics to extract, while high-density polyethylene plastics will be the most difficult to extract. These are my materials, and this is my procedure. And I prepared the solutions using a specific criteria of adding 55 to 60 milliliters of water, adding the plastics that are needed, pouring in the amount of requisite oil and magnetite powder, mixing and going through 3 extractions. I used 3 magnets for these tests, 10 microplastics, and 3 extractions per trial. My data shown here depicts exactly what I was measuring throughout the process. The visual effects of what happened to the water, the visual effects of the magnetite powder, the oil quantity, and how much plastic there was. The research that I based this on was a study done by high school student Fionn Furia, who was doing this based off of the current situation in Ireland. Throughout this process, he measured the percent decrease in plastics by type and by volume of oil used. He used a spectrometer and a microscopy machine. My conclusion. My hypothesis was proven correct by varying degrees of accuracy. By my own trials and testing, smaller fragments of pieces were often the easiest to extract, with the common exception of the yogurt container. Lightweight pieces, including the Ziploc bag and grocery bag, were also quite consistently easier to extract, aligning with my projection of low-density polyethylene being an easier plastic to extract. Throughout all the trials, magnets consistently cleared plastic bottles with little resistance. Where it diverges from accuracy is in comparison to the research used with a microscopy and spectrometer machine. These machines allow for specific percentage decrease in the total amount of microplastics, a much more in-depth explanation into this project's subject than my own. Had I have had access to these materials, I would have been able to more accurately describe my results. Through considering the project research of Thione Ferreira, my hypothesis was proven incorrect. Low-density polyethylene only saw an extraction decrease of 1.61% lower than that of high-density polyethylene. Polyethylene terephthalate was among the plastics with the least extraction rate. Many of his trials also resulted in a majority extraction rate of above 85%, as was seen in my trials. The laundry lint was an outlier in my eyes, as I believe that large chunks would be too unmanageable for extraction efforts, but his percentages show quite a different story. This project offers a glimpse into the future of microplastic extraction, an application of magnetism in a way that can not only benefit our planet, but set the stage for future advancement. Thank you.